Okay, hello everybody. Welcome to a tutorial for the first exercise in the LEAP training exercises, the general overview and introduction to LEAP. It starts on page 10 of the exercise booklet, and we're going to be working with a fictional country called Freedonia. And we're going to look at the energy system and learn how to build up a LEAP dataset from scratch. Freedonia is a strange country, and on page 10 it says that in order to illustrate how LEAP can be used in a variety of contexts, the data in Freedonia has been structured to reflect the characteristics of both industrialized and developing countries. So, for example, Freedonia's urban population is living at OECD standards, but its poorer rural population doesn't have access to modern energy services and heavily reliant on biomass fuels. So exercise 1, we're going to consider a subset of the sectors that we would generally look at in a LEAP analysis. The subsequent exercises add on other sectors to build up your experience in creating different branches and different modeling methodologies in LEAP. So the first thing we're going to do is to create a new blank data set. Freedonia is included in every LEAP download, but for this exercise we're going to make a new blank data set called New Freedonia. So after opening LEAP, we're going to click on New, and we're going to create a data set called New Freedonia. And then we're going to click OK. So we've now got a new data set called New Freedonia. And the first thing we're going to do is look at the basic parameters or the settings screen to select the time period that we want to look at for our analysis. So I'm going to click on settings, and I am going to, under the years tab, choose 2010 as my base year. It's already in there. 2011 is the first scenario year, so when I'm going to start my projections from. And I am going to set 2040 as the end year. So I'm going to change the end year to 2040. On the scope and the scale tab, in this exercise, we are looking at energy demand, the emissions and the energy consumption, and we're also looking at transformation, so we can keep that one checked. So I'm going to click close. So you'll notice at the moment we have under New Freedonia, we have key assumptions, we have demand, transformation, and non-energy. We're going to start off learning how to develop a model for the energy demand sector. So on page 11, it tells us that this preliminary demand analysis considers only the energy used in Freedonia's households. So we're going to be starting by developing a current accounts data set to look at the households in a most recent historical year, in this case 2010. We're then going to construct a baseline scenario to look at how energy consumption patterns are likely to change in the coming years without any new policy measures. And then in the last part of this exercise, we're going to develop policy scenarios to look at how we can reduce emissions and energy consumption by looking at energy efficiency measures. So the LEAP exercise then recommends that you spend some time thinking about how to structure the data based on the information that we are told about Freedonia households on page 13 and page 14. Once you've done that, we then want to create our different branches to describe the household sector. So to create a branch, we can right-click where we want to add the branch, so under demand, and we can create a new branch called households. And what we're told are that is that there are 40 million people living in 8 million households in Fredonia. Of these households, 30% are in urban areas. So we can now split our households into two categories: urban households and rural households. And I can begin to enter my data into Leap. So I know there are 8 million households. I want to enter this on this first branch here. That this is the first activity variable I'm entering. So I have 8 million households in total. So if I go over to units and click the three dots, I can then select household as one of my units. And I can then enter 8 as 8 million. I could also enter 8 million households. And it is the same, it is equivalent. In urban areas, I have 30% of those households. In rural areas, I have the remainder, whatever's left. Within Leap, we can represent the remainder. We could either enter 70, but entering the remainder is helpful because then when we create scenarios into the future, if we change the number of urban households, the number of rural households changes automatically. So then I have information about urban households, and it says 30% of urban households use electric stoves for cooking. The remainder use natural gas. So now I've broken down my households into urban and rural areas. Now to get my energy consumption, I am going to split urban households into different activities that take place. So I've got cooking. And I've got two fuels or technologies that are used for cooking. I've got electric stoves and I've got natural gas stoves. So now I'm choosing a technology that is used for this particular activity. So I've got electricity as my fuel, and I have electric stoves. And I also have natural gas. So I've got my two activities there. So now I'm also told that 30% of households use electric stoves for cooking. So I can put 30 there. And the rest use natural gas. And I'm told that each household only has one type of stove. So they have to add up to 100%. This is my activity level. I've broken down my 8 million households, 30% in urban areas, 100% do some form of cooking, 30% of those households have electric stoves, the rest use natural gas. So I know how many households use electric stoves or natural gas stoves. Now I need to say what the energy intensity is. How much energy is consumed per household using an electric stove or using a natural gas stove. So I'm told that the annual energy intensity of electric stoves is 400 kilowatt hours. So I'm going to change the unit. And for natural gas, it's cubic meters. So I have 400 kilowatt hours and 60 cubic meters. So now I've entered cooking. Now it tells me that urban areas all use electricity for lighting. So I've got another activity here, lighting. And I have electricity as the technology, as the fuel that is used. So they all use electricity, and they consume 400 kilowatt hours per year in 2010. Now notice here that in my urban households I have cooking and I have lighting, and it says percent share here. The percent share divides different activities into the percentage of households that do one and the percentage of households do another, and it expects them to add up to 100%. That's not the case for cooking, and it's not the case for lighting, because homes have both cooking and they do lighting. So the percent here should not be share, it should be saturation. It's what percentage of all households have this activity. We can have both activities at one time. So that percentage there should be saturation. Next, we're told that 95% of urban households have refrigerators. And they use electricity. So let's add in electricity. And 95% of households have electricity. So I can enter in 95% saturation. 5% of households in urban areas do not have a refrigerator. But 100% of those that do use electricity. So that's why this one is 100%. And the energy intensity is 500 kilowatt hours. So finally, for urban households, we then have other appliances. So I have an other category. And the fuel, the technology here is electricity. For TVs, for computers, fans, etc. Electricity. And here again, we have 100% saturation. Everybody has some other appliances, and on average, households consume 800 kilowatt hours per year of electricity from these other appliances. So now I've entered all the information about urban households, and I can move to my rural households. One of the useful features in LEAP is that we have cooking and we have lighting, refrigerators and others in rural areas as well. We don't need to spend time creating all of these branches. We can copy them. I can copy cooking from urban areas and I can paste it under rural. So now I have cooking, I have lighting, I have refrigerators, and I have other under rural areas. But if I look at the details, I find that the types of fuels that are used in the cooking sector are quite different. It's no longer electric stoves and natural gas. It is charcoal, it is LPG, and it is wood. So I'm going to delete electric stoves and I'm going to delete natural gas from cooking, and I'm going to add in charcoal first. So I have charcoal, I have LPG, and I have wood. So I have those three stoves, and then I have the table on page 14 which tells me what percentage of the rural households are using these different types of fuels. I have 30% using charcoal, 15% using LPG, and then the rest, the remainder, using wood. And I'm told the energy intensities as well. So the energy intensity of charcoal, the amount of charcoal that is consumed in these households, 166 kilograms per household. LPG, 59 kilograms per household. 525 kilograms per household. So now I have the activity level. I have the number of households who are using these different fuels, and I have the amount of energy that is consumed per household. This allows me to calculate the total energy consumption and eventually the emissions associated with using these different types of fuels. Let's see what it says for the other activities. It says 20% of rural households own refrigerators and other electric devices. So 20% of households own refrigerators and other electric devices. So let's have a look. Refrigerators, only 20%, rather than 95%. Other electric devices, also 20%. Refrigerators consume 500 kilowatt hours. So under refrigerators and energy intensity, 500 kilowatt hours, the same as in urban areas. Other electric devices consume 111 kilowatt hours on average. All rural households currently use kerosene for lighting, consuming 52 litres per household on average. In addition, 20% of rural households have electric lighting. So all households use kerosene, but some also have electric lighting. So let's represent that. We need to add one more fuel that is consumed under lighting, kerosene. Let's add kerosene lighting here. And then in the lighting sector, for kerosene, there are 52 litres per year for each household that is using kerosene for lighting. 52. Now let's get our activity levels right. So 100% of households have some form of lighting. 20% of them have electricity, and 100% have kerosene. Now in this case, we don't want electricity and kerosene to have to add up to 100%, which is what happens if we have percent share. In this case, saturation is more appropriate because we have both of these fuels being used in these households. So having done that, we have now created our representation of energy consumption in households. And on page 15, we can begin to look at the results. So I'm going to click Save first, and I'm going to click on Results. Do I want to calculate? Yes. Now to get the table on page 16, we have the different fuels along the top. So I'm going to click on the Table tab, and I have my different fuels along the top. So where it says All Years here, I'm going to click on All Fuels. So that gives me the different fuels along the top. And I'm going to click on Levels here to increase the number of branches to get the correct number of to replicate the table that I have on page 15 of the guidance. We can now see the energy consumption in different sectors. If I click on subtotals, I then get it the same as in the table. And what I can see is that I've made a mistake. The number here, 69.1, the total energy consumption, doesn't match. And I can look and see why it is different from page 15. I can see that in urban areas, the energy consumption, the total energy consumption of 19 is the same as in the table. But in rural areas, the 50.1 is different. So let's look at why that is. Cooking, 35.5 is the same as in the table. Refrigerators and others is the same. But lighting is different, 12.2 compared to 11.2. So I've been able to go in and identify where it is that I've made the mistake. Let's go back to lighting and see what I might have done wrong. So it tells us that all rural households currently use kerosene for lighting, consuming 52 litres per household per year. I've got all households using kerosene for lighting, 100% saturation. 20% have electric lighting. That's true. Consuming 150 kilowatt hours. So that's where I've made the mistake. I didn't change the energy consumption for electric lighting in rural areas compared to urban areas. Now if I click on results and go back to my table, I get the same total energy consumption, 68 million gigajoules. Okay. On page 16, we have the second part of our household analysis. We're now going to create a forward-looking scenario for the period 2011 to 2040. This is going to look at how household energy demand is going to evolve over time under current policy conditions. First, we need to create a scenario for the baseline. To do that, we click on Scenarios. We're going to add a new scenario under Current Accounts called Baseline. Now we have the scenario for the baseline. And at the bottom of page 16, we're told about the assumptions that we have in our household sector. So for example, it says by 2040, 45% of Fredonia's households will be in urban areas. So I'm going to go from current accounts and change the scenario to baseline. And it's very important to remember which scenario you're in where you're entering data. It's a common mistake that people will enter data in the wrong scenario and have to go back and change it. So we're going to change to the baseline. And we're going to change the percentage of people that live in urban areas. But before we do that, we're also given information about the number of households. The number of households is expected to grow from 8 million in 2010 at 3% per year. Here we're going to use one of the common expressions in LEAP, growth. 3%. So this growth expression says take the number and apply a percentage increase to it. And we've added in 3%. That's why we get this graph where the number of households is increasing at 3% per year. Our next piece of information is that the number of households in urban areas are going to increase to 45% by 2040. In this case, we're not applying a percentage growth rate. We know what the value is in a particular year. We know what it's projected to be. And in this case, the function to use is called interp. So if we use interp and say by 2040 it will be 45%, What LEAP does is draw a straight line between the last value, in this case 30%, and the value in the year that is specified, 45%. So we can see that gradually the number of urban households increases and the number of rural households decreases. Let's look at the other aspects of our baseline scenario. In urban areas, it says increased preference for electric stoves results in a 55% market share by 2040. So let's look at cooking now. Electric stoves, 55% will be electric by 2040. So again, that's the same interp function. By 2040, it will be 55%. The energy intensity of electric and gas stoves is expected to decrease by 0.5% every year due to the penetration of more energy efficient technologies. So the energy intensity, how much energy we consume for these stoves, is expected to decrease by 0.5% every year. So here we can use the growth function because it's a percent change, but we apply a negative growth, minus 0.5%. And the same in the other one, minus 0.5%. Now that may be counterintuitive because we've got the growth function here, but we can have negative growth. We can have a decrease by putting the minus sign in front of it. Finally, the next change is that as incomes rise and people purchase larger appliances, annual refrigeration intensity increases to 600 kilowatt hours per year. So it was 500 kilowatt hours in 2010, 2040, 600. Similarly, annual lighting intensity increases to 500 kilowatt hours per household in 2040. So in lighting, we're at 400, and that's going to increase to 500. And finally, other energy-using equipment grows rapidly at a rate of 2.5% per year. So here we have growth, 2.5%. And we have a 2.5% increase every year. So now we have done all the changes in our baseline scenario with no new policies for urban households. For rural households, the share of cooking devices in rural households changes so that by 2040, 55% of households use LPG and 25% use charcoal stoves, and the rest, wood. So this is under our activity level, and we want to say that by 2040, 55% of households use LPG. You can see that that blue part of the graph increases. 25 use charcoal, and the rest use wood. So the real change is the increased uptake of LPG. The number of rural homes using refrigerators, lighting, and other devices is expected to increase to 40% by 2020, 73% by 2040. So now we have 2 years where we've been given a specific value. So we've been told that the number of households using refrigerators So we're saying interp 2020 40%, 2040 73%. So this expression here, the interp expression, we can enter multiple years with multiple values. We don't need to just use the end year or anything like that. We can enter in midpoints as well as we create our scenarios. And we want to enter the same expression for other. And we want to enter the same expression for electric lighting. So we don't want to enter it here for lighting, we want to enter it under electric lighting. As we increase the number of households using electric lighting. And accompanying that change, that increase in electric lighting, the fraction of rural households using kerosene for lighting is expected to decline to 60% by 2040. So we've got this change occurring in electric lighting too. 2040, 60%. More people have electric lighting, less people need to use kerosene. As incomes increase, the energy intensity of electric lighting is expected to grow, reaching 300 kilowatt hours per household on average. So at the moment it's 150, but as more people get electric lighting, it's going to grow to 300. And that is our baseline scenario for the households sector. So if I then click Save and click on Results, I can look again at my table to make sure that I have the correct energy consumption. So if I look at the second table on page 18, to create that table, now my columns are not the fuels, they are the years. So I'm going to put every 10 years here. And I can see that my total energy consumption is 183.6, exactly the same as in the exercise. So that suggests to me that we have entered the data correctly for the household sector. So we now have historical energy consumption for 2010 and a projection into the future for the household sector.